So now we're going to talk about the, again, application of the linear models to regression, but not only linear models. We're going to see a little bit what is the random forest. And with that, I just want to make a little comment, because there was a little question about causal relationship in the data. I mean, not the correlation, but the causation. And essentially, I don't think that is that important per se. It depends, again, what do you want to predict? But the idea is like, if in your data, you have, some attribute A, and only if attribute A have certain value, attribute B will have another value or something like that. So if you have a causal relationship in your data like that, there are these structures which you are going to see now, which are called random forests, or they're started from the decision trees, which pretty nicely will handle it, because the decision trees, you all seen the decision trees when you try to call, I don't know, DISCAM, and to ask somebody, you ask, oh, do you have this problem, press this button, do you have that problem, press that button, do you have this problem, press this button, and so they trying to channel you when you call your bank or something like that. So, and decision tree works kind of naively in a similar way, so that it splits your data as a function of your kind of input parameter. So kind of like several branches could end up with with the right answer, with the right estimator. And from this point of view, you can, and kind of the better versions of them, they're based not just kind of go to the left or go to the right. There are some principles which are related to the informational content in your data, or in particular it's related to the entropy. So how you make your splits on your tree. And but if you have a lot of attributes, these trees, you can build them in a random fashion, and you can build the ensembles of those trees. And that's what we're going to talk about. But kind of, you can just understand that kind of like, even if there is a causal relationship in your data with these kind of forking decisions, so that if feature A is greater than something, then we get in this branch that take care of some causal relationship in your input. So I think that at least that's how I see it. I'm not sure if there is anything more to that. Okay, and there was one more comment that somebody wants expert in machine learning in the metabolomics and proteomics, but yeah, I think that's a little bit challenging. Okay, so let's go for this. And what we're going to do here, we're going to analyze one of the standard data sets. And that's, by the way, yes, there is very famous UCI machine learning repository, which contain a whole bunch of data sets. So if you want to train machine learning and you want to see one of the ways, of course, you can go to Kaggle, but you can, if you think that, oh, in Kaggle there is too many solutions for the given problems which you do not want to look up and you want just to see it for yourself from the scratch. So you just type in the Google UCI machine learning repository, you'll get to this website, and you get a whole bunch of data sets which have a nice description, and I think they are all relatively small data sets. Okay, some of them are relatively large, but different size data sets, and you can try and do what we're doing now. And I think we'll choose a data set from here to try to do it just now. Okay, so, but let's go into this example, and this example is also coming from that data set, and the data set is dealing with the wine quality. Yes, so kind of the wine could be characterized with the different properties, that there is, acidity, residual sugar, and all the rest parameters, and you can say what is the quality of wine, how the people how you can evaluate it. And the idea is that we want to develop an algorithm which could predict that. Okay. So we need to import all the standard things. Yes, we need a NumPy, we need pandas, we need this from scikit-learn, we need this forest regressor, which I just mentioned, and I will tell you a couple of more words later. We need the linear regression, and we need these two guys, and they are also linear regressions, but with linear regressions with the bells and whistles, which are very useful. So they are the linear regressions which can do certain types of regularization and cross-validation. We need, for the metric, we need our mean squared error. And for the model selection, from the model selection, I've been asked, how we can choose the hyperparameters, kind of how can we optimize lambda from the regularization in a nice way. And other parameters, we're going to do it with using the function which is called the grid search, but this is not the only function which is available for this kind of operation. So you have other options. So because the grid search will indicate the branches of the parameters where you need to evaluate your model, and the algorithm will just go through all options and search. But if you have too many parameters, and even if they have a little range, of course you can search forever. From this point of view, one can do not only grid search, but you can also, there are some random versions, but we're just going to look into the documentation just now. Let's first go to the for the vanilla version of this notebook before breaking it. Okay, so we need a cross-validation score, test train split, and we'll need this thing, which is called standard scalar, which I already mentioned before the break, that we need to, in order to be able to do some reasonable statements about importance of the of the input data, or kind of parts of the input data, or of the features, we need to be able to say something. In order to also train model in a little bit more predictable way, what we need to have, we need to bring all the features so that they are on the same scale. And there are several pre-processing routines, and you can just check what here we have a. Now this is a model selection, and where is processing? Oh, probably I misspelled. Yeah. Yes, and there is a whole article in the scikit-learn about what preprocessing could be done. Yes, there is a standard scalar. There are some other scalars, or there are some other ways to do the scaling. Yes, there is a min-max scalar, and max upscaler, and so on. So there are several options how you can prepare your data, but what we're going to use this standard scalar. And what the standard scalar is doing, we can also read it here. The standard scalar is bringing your data to its kind of Gaussian, or kind of to the zero mean, and the kind of like it's been generated from the Gaussian distribution. So we're subtracting the mean from the data and dividing by standard deviation. Okay, so let's go. Okay, so there is a question about the previous one. For linear regression, yes, there's no appear to be a linear relationship between price with average number of bedrooms. Would the inclusion of this feature result in overfitting all the same artifact? Ideally, should this feature be excluded from? That's a wonderful question. You can try. Just drop that column and see what is your performance. But there is no linear relations, because this is a single kind of more or less kind of it's not continuous feature, or kind of it's average. But let me see, where is you mean graph like this? Yes, the average number of bedrooms, because you see it's clustered by itself, but you can still imagine that it's okay. I wouldn't say that it's yeah. But that's a nice little task. Just drop this column, average number of bedrooms, and check whether, because you'll probably have the similar relationship between average number of rooms is more everywhere. Yes, okay. And just check the performance. I think that's a very quick task to do, and we can try it just now. Okay, so this we've done. Yes. Okay, so now we can go and get this wine quality data set. So, and what is here? We get here different features, yes, which means some properties of the chemical content of the wine, and we get some quality score. Okay, the first thing which we can try and check, which is always nice, is just to see that there is no missing data. This is very good, because again, I wouldn't repeat it again, so that yes, because if there is a missing data, we need to decide what we're going to do. And there are several strategies to deal with that. Do we want to fill up this data, or do we want to drop the inputs without data and things like this? So this is up to you as the person who is implementing the algorithm. So we can do the same thing with the, as in the previous example, we can plot the data and plot the correlations to just see what are we getting. Okay. And there are a bit more entries that takes a little bit longer. Okay, yes, but okay, we've seen it already. It was here, and you can see that, you know, it looks like in some cases there is a correlation, in some cases there is much less correlation. Like, for example, in this case, it looks like there is a little correlation, but like in this case, it's almost no correlation. So yes, you can see that some features seems to be, there is a correlation between them, between other features, there is none. And we could get this formulated a little bit more formally in the correlation metrics. Yeah. And here we have corresponding, a corresponding entries, which are saying that, okay, the density, whatever it is highly correlated with the mark. The content of the sugar is a little bit anti-correlated or almost no correlation. The same with the citric and acid and so on. Okay. So, but this is just, you know, a statistics to give you an idea, okay, where we want to go with that. Now let's do the split. And because here I mentioned to you that we're going to do the transformation. So what we do, so Y data, so which we want to predict, is our quality column, and the X data is all the rest, if I'm not mistaken. Yes, X data is all the rest. And how we can do it, we can take our full data and just drop the column Y data and the axis Y, yes, because that will axis 1, because that will be this axis 0 will be this axis. Okay, and now we just do the split. Train, test, 30%. And afterwards we do the scalar. And how we do the scalar, and I think this is good rule to do it kind of like this without, if you don't know much about the data. So we train scalar because it will be a Gaussian mean, because what is the standard scalar? It will calculate the mean of your corresponding column and subtract it from every entrance and variance and divided by the standard deviation. Yes, from variance you get standard deviation, so divided by standard deviation. So in order not to contaminate, contaminate the training data with the test information, we calculate the mean and the standard deviation on the trained data and transform it. And also what we transform with the same mean and the standard deviation trained data. Okay, and now we can do what we just did. Yes, we have linear regression and we do linear regression fit, and we can calculate some standard metrics on the trained data and on the test data and see what is the mean squared error. And we see that, okay, it's equal to this. Okay, or we could, for example, we could probably do also R2 squared error if we want to. Let's do the R2 score and tell me what the R2 score is, because we're having a tutorial. Let me stop share for a second. And where is the R2 score? Come on, just go to the previous notebook and put it together. Have we got the answer? Come on. Come on, guys. Are we getting there? Or have I lost connection to the Slack and you already answered 20 times? Okay, so the problem number one was that we don't import it, so we just add in from scikit metrics import R2 score, yeah. And now I just copy. You see the line from, and that's how you need to think about that. I mean, we just did it in the previous notebook. Let's just copy it, yeah. And it's have the same, absolutely the same input, yes. Test predictions, test predictions and train predictions of corresponding ones, and that's all. So we do it, and that's what we are getting. Just make sure that you can do it. Are you with me? Okay, good. So, and judging by our previous example, R2 score, this R2 score doesn't look very impressive, yes. But at least, there is a logical thing. It's 0.29 for the train, and for the test, it's a little bit low. Okay, good. Very good. At least there is this consistency. They're comparable, but they are bad enough. So we might consider better model or doing something better with this model. Okay, so good. So, but I was asked also, can we separate importance features? And now we could very easily separate the feature importance, because all our input values are comparable, and it means that the feature importance will be just scaled with the size of the coefficients in the linear model. So it means that the density is the most important feature, and afterwards residual sugar, and afterwards acidity. But this would be also rather intuitively understandable from this matrix, yes, because we have a highest correlation. So first of all, the density and residual sugar is correlated, yeah. So we get the highest correlation, and just give a look on this correlation matrix and what is correlated to quality, and we can get a pretty good idea what is important and what is not important. Okay. but this is kind of a little bit more formalized way. And now what we're going to start doing, we're going to start playing around because, and I was also asked a question kind of about regularizations. Okay, now let's do the regularization. But the kind of naive or straightforward linear regression doesn't have regularization built in. For that, we need a model which is called lasso. And this will be a model with a, I think, L2 regularization. And let's see, oops. If we don't know what it's do, we can always Google. And that's what a very important lesson for you in real machine learning, that 99% of the questions which you have, you are not unique unless you're doing something extremely unique, which is possible, but not a common practice. So it means that 99% of your questions have been answered by somebody already, or at least there is another struggling soul somewhere on the other side of the world, and you can always ask the person what is his progress. Okay, so let's see, linear models, lasso. What the lasso is? Lasso is, okay, it's L1 regularization. Okay, so what the lasso is doing, it's doing for us, and assume you could see my Firefox screen, yeah? Okay, so what lasso is doing, it's doing our linear model. This is linear model, and alpha W1, this is regularization term. And we immediately could see what will be the meaning of this coefficient alpha. And what is also very important and very useful, usually, at least in the documentation to the scikit-learn, or if you do the neural networks for, I don't know, PyTorch or TensorFlow or Keras, you will have like a very naive and useless example. But what is the beauty of this example? You can get the sense of what is the typical scale of the parameter for the normal parameters, you know, kind of. And you see, by default, they're choosing alpha 0,1. So it's not a bad idea to be somewhere in that range, or we can try to find what is the best alpha for our purposes. Okay, so now let's do it. So, and here we try alpha 0,01. Okay, it's very weak regularization because, again, from the one hand, we've seen that here by default they're 10 times larger, but let's try. Okay, so we just, again, the same. Lasso is a lasso with the parameters, and lasso fit. Good. We get our model. We can get the feature importance. Yeah, and we can also try to predict something, because here we already go into another lasso. We try to find the optimization of the lasso, but okay, we see that, okay, also the order of the features change. So we add regularization and something happens. So if we want, we can play the same game with the prediction, and let's probably do it just for practice. And afterwards, we'll see how we can optimize and find the best value of the alpha. But let's see what's happening here. So how do we predict the lasso? We predict in the same way, yes, like here. Let's first do the mean squared error. Where is my lasso? Oh, but here, what we need to do, we need to make sure that we are substituting the right model. No, lasso 1, lasso 1. And okay, so this is a mean squared error. Let's see how it's compared to the other one. It's comparable, roughly speaking. Okay, but let's see what's happening to the R2. Where is my R2 code? Just make sure that we get the right model. Okay, R2 is also comparable, but not very impressive. But now the question is, like, you know, maybe it's because it's a very weak regularization. What if we try the bigger regularization? But how big? And that's where we need a little modification of this procedure, which can do regularization, and it's called lasso CV. And CV is for cross-validation. And that's already is getting interesting. But before we diving into that, let's give a look. What does it do? So linear model, lasso CV. And again, what does it do? It's do absolutely the same, but it's also with the iterative finding along the regularization path. So what's to do? So it could help us to find what is the best alpha. Yes, and also it's also have a built-in order to find what is the best alpha. It can also do by default, we can turn it off, CV none, or by default, we can turn on cross-validation. Okay, and we get all the parameters which we could specify. So do we have any? Okay, so nothing happening in help. There is several options, or there is no questions, or you are lost, or I lost my connection to Slack. Okay, so let's go here. So and now what we have, now we need to specify where the system needs to go, which alphas to try. And there is a nice choice, yes, kind of the alphas. And usually because you don't want to try 0,01, 0,02, 0,03. So what you do, you would do it in the powers of 10. And let's, before we run it, let's just try to see what's happening here. Who is this? Just to know, no. What are we going to get? We're going to get from the 10 to the minus 6 to the 10 to the square. Yeah. So this is our 100. And we're going to get the split over the 200 entries on the logarithmic scale. Yes, on the exponential scales from 10 to the minus 6 from very, very small alpha to 100. So 200 entries. Okay. So, and we're going to evaluate for each of these 200 entries. We're going to evaluate our model, and we're going to do a 5-fold cross-validation. Sorry. Okay, and now kind of that's all. Now we just do it and wait. And you see, because it's a very simple data set, small data set, and straightforward algorithm, it's done extremely fast. So now what we can do, we can get what is the nice alpha, and what this algorithm is telling us that the very small alpha is very good. Okay, so we have probably the reason to believe the algorithm, and in principle, what one can extract from this model, one can extract all the metrics and just plot it as a function of alpha and see, you know, which is it really the best or not. Okay, so and what we can do now, we can do again, look at the feature importance, and you see in this case we get again that our density is the most important feature. Okay, and after we've done that, so after we've done optimization of our regularization, we can check how our model is performing. Okay, and it's again performing in a very similar way. Okay, let's also add the R2 score. Okay, yes. So, and what is really clear from here, from this part of the tutorial, that a linear model is not the best one for this data set. This is just, you know, a definitive statement, because we try, maybe we can also try L2 regularization, but for that we need to go to this, if I'm not mistaken, to this model which is called let's go to the linear models. Yes, and this will be, yes, ElasticNet. So and it's do the both regularization. So it's doing L1 and it's doing L2 regularization. So and we can try and see it. But very often, you know, in the real life, because you don't have to do linear model, you know, your choice is any model that works. You just what you want to choose good enough model and not too complex enough, because obviously this problem could be solved by the, you know, 50-layered neural network, but you would train it from here till kingdom come, because kind of it takes time to train. Okay, so but what we can do next model, which is called random forest, and essentially kind of, as I mentioned to you, how these random forests are working. It's a decision tree. So it's kind of it's constructed and using the informational content in the data, and it's creating forks in the data set in the point when the there is a corresponding change in the entropy for the corresponding split, and you do it for the many enough for the large data. You just do it on the large enough on randomly generated trees. Okay, let's look on the random forest regressor. Okay, so, and what we see, so first of all, it's an ensemble method because it's a forest method, but it will be a collection of random forests. By default, it will build 100 trees. So you can increase this number, but in this case, 100 is good enough number because you don't want to be that your number of trees is comparable to your data size. You want to be number of trees to be smaller than your data size, otherwise you will overfit. And we have, how many data points we have? We have 5,000 data points, 100 trees. That should be okay, because that's a parameter which we can choose. And it's, as simple as, again, we have random forest regressor, random state, and we do forest fit, X, Y, and that's all. And our model is ready and is getting trained. Okay, so now we can see our errors. What is the mean squared error? And there is one more interesting thing. So we can do mean squared error, Y train, X train. Yes, forest predict. So this is the error on the train data. We can do the error on the holdout on test data. But also what we can do, we can use one more function in between, and we can do cross-validation on the train data. So we can train and we can do some cross-validation here and just see how that works. Okay, let's see. And this is very interesting, but it will take a little bit of time. And meanwhile, we can give a look into the cross-validation score because we don't specify it. And there is a question, what is it by default? And by default, yes, cross-validation score. Where is the default? No, how many? Yes. By default is a 5-fold cross-validation. So if 5-fold is not good enough for them, we can increase the number of folds. The optimization technique can be also done using the cross-validation. Yes. How does the random forest regressor differ from the classifier? I mean, this is a very simple thing, and that was okay. Let me just show you one slide, or let me. Do we have some fancy picture here? Because essentially, when you just imagine. Okay, let me just explain it in words. So, what is regression problem? Regression problem is that you need to predict the value of something, yes? But what is a classification problem is to draw a line where you say, everybody who is here is a class 1, everybody who is there is the class 2. So, and that's the only difference. So, but that's why you can do both regressors and, I mean, for all these methods, random forest could be regressors and could be classifiers. Like also linear regression, you can use for the classification as well. But in that case, what you want to draw a line between the classes. And in very easily, it is done by the procedure, which is called, for example, support vector machine classifier, because in that case, there is a very nice also graphical interpretation of the classification. Oops, where is my Slack? Okay. So there is really not much difference from just the difference, how you interpret the data, and very often how the regression, how you can turn regression to classification is very simple. You do the following job. You make sure that your output values are between 0 and 1, and afterwards, kind of what your regression will give you, it will give you something like which kind of number between 0 and 1, and afterwards you say, if the number is below 1/2, it will be one class. If the number is above 1/2, that will be another class, and that will be conditioned on the training of your classifier. So you take a regression model, you constrain the output data by the scaling, and afterwards you just say, okay, so in the training procedure, one class will be if you're above 1/2, and another class will be if you're below 1/2. Okay, so okay, and it was also okay. Sorry, I need a bit more clarity on this. When CVs perform, the average R2 is obtained. At what point do I determine if my model overfitting? Is the appropriate gap range between CV average R2 test, and that suggests that the okay. Okay, so when you perform cross-validation, you can get R2 or mean squared error, or whatever your metrics. And what you wanted to see, that value, kind of like when you will overfit, when that value or average of that value will be very, very good on the training data, but very bad on the test data. In that case, you're overfitting. Or kind of, so if you do it in with cross-validation, yes, so yes, you can compare the R2 average on the training and R2 average on the validation and do the same game, and only afterwards go for the testing. Because if you are overfitting, in that case, R2 on the train part will be much higher than the R2 on the validation part. Because if you get a large variance between the R2, so if your R2s inside of cross-validation are very different, it means that there is something inside of your data which is being mixed up. Okay, and how do you know that the 5 cross-validation score is good enough? I don't. You just try 5, and if you think that, and for the you can try 7 and afterwards 10, and you can see that how that affects the performance of the model. Is there specific acceptable range? No. There is kind of like, I mean, please understand, it's like it's not, because it's only meaning kind of like, you can decide that are you overfitting or not overfitting by, predicting unknown data. And kind of like on some stage, you need to say, okay, I train good enough model and I play all the tricks to convince everyone, including myself, that this is good enough performance. And that's why you do all this, you give the cross-validation things and things like this. When I use mean absolute error and when I use mean relative error, I don't know. It depends on the problem. When the problem is good for that, when that would be a standard metric for the error in that problem, I don't think that there is a definitive rules, but it's all for the regression, yes, because for the classification, there will be different metrics. Okay. Okay, have I run this or not? Okay. Okay, it takes a little bit of time because it's doing 5-fold cross-validation. And you see, we get a very interesting thing here, because we get the performance on the train is quite nice, yes, because mean squared error is quite low, but the cross-validation performance is much higher. So it's mean that Probably also there might be some peculiarities in the data. However, the test data performance is better here, but is better than cross-validated performance, but much worse than the train validation. So it's mean that probably we're a little bit overfitting in this particular case, because probably there is a little bit too much leaves. And what we can try doing, let me see, is it going to be optimized for the number of leaves max? Yes, okay, so we will not optimize for the leaves, but the max depth. Okay, yes. So now we're going to tell how to address that. Okay, but I mean, the naive thing which one can do here is to try to constrain the number of leaves, because from what we see, maybe it seems like 100 leaves is a little bit too much, and estimators is 100, and we can just maybe decrease it a little bit. Okay, and that didn't help us. So it means that we need to go now to the next step, which is try to play with the ranges of the parameters and try to optimize them. Okay, so is there a way to determine which models might be more accurate for the data before using the particular model? Yes, I mean, okay, partially yes. So the idea is that that's why you need to plot the graphs and see how they look like. So if you see that your data is more or less aligned along certain directions, it means that the linear models will work very well. And also there is but it's already in the sense of not urban legend, but like people are saying that, okay, if you have a more because what we're having here as the input parameters, we're having just the real values. Yes, where is our data set? We have acidity, alcohol content, sugar content, and so on. This is just the real number. But if your input parameters will be different, for example, what is called categorical data, which means that or you have you can be in discrete values. In that case, it is known that the certain, for example, ensemble methods works than the other methods. And the categorical data is, for example, you need to indicate in some questionnaire your gender, yes, and that will be male, female, and whatever other options, or your marital status. And the question is how you will transfer that into the something number-wise, and there are different ways of how you can do it. So you can transfer, all possible options and enumerate them, and take away the column with the, married, not married, divorced, and so on by the corresponding number, or you could put all zeros except one column, which with one entry one, which will indicate, married. Next column is, single, and that will be one only for those who are single, and for all the rest zero, for example, if we're talking about people. And in that case, I think there is a understanding that certain classes of forests works better, which have some special names. For example, there is a cat boost, which is working very good with the there is a boost in tree method, which called cat boost, which works very good with the categorical data, better than, for example, some other fancy tree boosting method that, for example, XGBoost or LGB, or what is called the Microsoft one, I don't remember, LGB boost, I think it's called. But essentially, you just need to start doing things, see, and also one could go to the places like Kaggle, where the people will discuss, okay, typically for this type of data, this works better. And this is, again, there is no hard rules, it's just, it's experience. People do it, and they have this conclusion, oh, this works better, or this works not, this works good or not as good. Okay, so where we were on the CV search, yes, no, okay. So, and this will take a little bit of time, because what we are now going to do, we're now going to say that, okay, the default parameters of our forests are not optimal because we are not getting the nice data. And what we are going now to do, we're going to consider the parameter, which is called max depth and max features. So what is the max depth? So no, I'm in the wrong, yes, here. So max depth is the maximum depth of the tree. It means that, you know, how many forks it might have. And the max features, and you see there are a whole bunch of different extra functions which you can optimize. Max features, the number of features to consider when looking for the best split. So it's when I told you that information content, which is related to the entropy, when one calculate the entropy and decide whether you need to split in this point or not, you need to calculate the entropy of the over the certain part of the data set. And so using this, you can do some limitations on that, at least if this tree is built on the entropy, but it should be. Oops, okay. Okay, let's run the, is the way to determine which models might, okay. So that was already, yes. Yes, and there is a good answer, which is saying that, yes, depending, it depends. Okay, good, let's do it. And so what we're going to do, we're going to look into the max depth from in the range from 10 to 25 and max features from the range from 6 to 12. Yes, and what that's going to do, it's going to evaluate random forest regressor for each of these, kind of, it will be the square grid, yes, for each of these values. It's going to do it based on the cross-validation 5. And the important parameter which one keep in mind before you do it, otherwise your computer will freeze and you will not realize that it's frozen, is this n jobs. And this is going to use how many cores of your processor is going to use. If it's -1, it means use everything what is available. And if it's like, but if you, for example, want to use computer in the same time for something else, you can specify, if you know how many cores you have, that you could use only 2 cores, use only 8 cores or whatever. But in that case, keep in mind that that might take a little bit longer. And afterwards, it's the search is done. We can treat the best locally found forest into our model. And let's try, and hopefully I will not, the Zoom will survive that. Is anybody else on call out of the, no, okay, let's see. Okay, because now I see that my processor is spinning. Okay, so do we have anything in the chat? The model predict very well when the turning the. So it's a question, yes. So a model predict very well when determining the hyperparameters we obtain a cross-validation score close to 1. I mean, if it's R2, yes, it's that. Or at least it's an indication that that's, yes, if it's a prediction on the test data, which is unseen and haven't been used for training. Okay, so we're done. So we get our grid search, and we can also give a look. Yes, okay, we see that the keeping the same random state helps, because if the random states were different, these numbers might be different. Okay. So now we get the best possible max depth and best possible max features, and we can check again here that, you know, where is the max depth? By default is none. So it means that it's do the, yes, if none, then the nodes are expand until all leaves are pure, or until all leaves contain less than minimal samples states. So kind of like, but we find that what is the best possible max depth for this particular problem, and what is the best possible max features. Okay, so now we could see what is the performance. Okay, so, and we get the mean squared error, which is a little bit lower. Yes, if I'm not mistaken. Yes, we get a mean squared error, which is a little bit low on the cross-validation, and on the test, it's pretty comparable. And what we can also do, we can also do the same game for the R2 score. Can we do it to the video? Because here we can definitely do the R2 here. Where is? But now the question is, okay, let's fix this one. And let's also see, can we change the scoring for R2 in the cross-validation? Okay, so where is the cross-validation score? Cross-validation score, scoring, still, okay. Okay, so we need to choose a single metric. And okay, let's just try and see what's happening. Can we just write R2 score here? R2 score, and we'll see just now if it works or not. Yeah. Okay. It doesn't work. Okay, you see. Let's see what are the valid options. Okay, how my scikit is called? Because I don't import the scikit. Okay, good. I import only these two functions. I import only functions which I need import. Skip learn metrics. And let's do something like this. Okay, good. So now we get the list of possible score names, and let's see, do we have, it's called just R2. Good. You see, so it's not that it's not supporting, because I just meaning that I don't know how to type it. Okay, good. Okay, perfect. So now we get our R2 score, and we get a R2 score on the test set is 0.53, and then the cross-validation is comparable, but a little bit larger. Okay, and we can also, again, give a look on what is our best feature importance in this case, and what we get that the density is not that important, important according to the what we found, that the alcohol content is most important, and afterwards acidity, sulfur oxide, density, and so on, which is a pretty, yes, which is a, how to say, pretty disappointing to say that the wine is better if we have more alcohol. Okay, so any questions to this? Okay, please, what is the spec of your computer? Taking a bit long here. Okay, no, I've got the MacBook Pro, but quite an old one from 2019. Okay. So what else we can do here, or how we can? So I wanted to try something else. Yes, I wanted to try. Okay, yeah, let's try to play this game, but with another search in the grid, because again, we still was searching very constrained list of features. Let us go to the grid search CV, but instead of grid search, let's do some random search, and let's increase the range of parameters. Okay, so grid search. But now what I want, okay, no, let's go here. Where we are, grid search, parameter grid, run. Yeah, I want this one. I want to show you this one. Okay, so I suggest let's try to do the randomized grid search, because why it's better? Because when it's doing a grid search, it's looking the full space. And, you know, in this case, you've seen it takes some time, but according to the comments of people in the chat, you know, it's take quite a bit of time. And if you increase the search space, suddenly, you know, you get a problem, because suddenly, you know, it takes longer and longer and longer, and it could search the space without any luck. And so let's try to do the same game. And let's try to do it kind of what can we search for? Okay, let's see. Let's go back to the properties of the forest. And what we can search for? We can search for number of estimator. We can include, increase, or kind of they include max features. Okay, I mean, I think that will be good enough. Let's do the number of estimators, max depth, and what else we were looking for? And we were looking for max features. Okay, so let's do something like this. But also what we need to add number of leaves, and it's reasonable to start leaves, let's say from 10, and go in, what can we do? Let's go in tens. Okay, so what do we need? We need something like, so we need to do range. Yes, we start from 10 to, let's do 200 in step 10. Yes, would it give us, okay. Would it give us the right thing? Okay, so let's do something like this. Or maybe step 10 is, maybe we can do step 20, but we can do a little bit more. Something like this. Hopefully I wouldn't kill my computer. Okay, so let's do like this, but we do it randomized, so it's not going to implement it in every point. But if it will dies out on some, or kind of it will take, if it takes too long, we'll just kill it. Okay, so what is the proper, yes, n estimators. So now let's add here. Probably we need to add it from this side in order. N estimators. Now we add it like this. And I'm forgetting semicolon, yeah. Okay, so now we've done that. This we can delete, and now we just copy this guy. Where is this guy? Okay, but now instead of grid search, we need to put our randomized search CV, and let's see if I crash it. I crash it. Take it 10. Okay, CV5 locally best forest fit. Okay, let's call it locally best forest fit R to indicate that it's our randomized forest or randomized search. And okay, let's try. Oops. Ah, okay, yes, because I did not import it. Sorry. Let's go up and then add it to the imports. Yes. And we can, this guy. Okay. Okay, next. Okay. Okay, good. invalid parameter and for estimated random forest. Valid parameters are bootstrap. Okay, interesting. So we cannot. Okay, good. So it's mean that we cannot change the number of estimators in this way. Oh, that's quite disappointing. I was thinking that we can. No, n estimators. What's wrong with what I'm doing? Am I doing a mistake? Yes. Sorry. Yes, this is a mistake. I have a semicolon inside. Okay. So you are also welcome to do it, especially if you do it on the Google Colab. I think those computers should be fine. And let me see what's happening. Okay. Okay. Wow, it wasn't that long. Good. And now we need to check what are we getting. Are we getting any better or not? Okay, so no, this is the wrong estimator. Okay, so number of estimators needs to be increased a little bit, but the result is, yeah, it's not that impressive, I think. Okay, let's do the mean squared error on this guy. Okay, so all that compute for nothing, essentially. Yes. Okay. 0398, 0366. Yeah, it's even grows. What's happening to R2? Have we got any improvements? Okay. Okay. Are we getting improvements in R2? Not really. So you see, sometimes you do, but you haven't reached too much. So that might be indication that probably, or we haven't searched well enough the space, or maybe, random forest is not good enough to solve this problem better. So what we can try to do, because it's quite fast. I mean, let's do something like this with a step 40. Yeah. Let's see. Okay. No. Okay, no, it's increased the number of leaves to 500 and something, yes, but it doesn't really increase too much the efficiency. Yeah, probably the forests is not the best approach to this problem. And one more thing which we can try to search here, because we're here using mean squared error for scoring. Let's use R2 for scoring. Oh no, not here. Sorry, here scoring. Let's do it like this. Oops, not really. It's even more estimators. Okay. Yes. Okay, good. Okay, so yeah, what we can see that yes, we were trying as much as we can, but let's see the same thing with the feature importance, with all our. Did the feature importance have changed or not? No. So alcohol is a key factor. Still key factor, the alcohol content in the forest's performance. Okay. So are there any questions in the chat? No. So just, you see, kind of like this wasn't in the original notebook, this random search, but just add and just play around and you'll see, does it work or not? And as we see in this situation, kind of, it doesn't really work perfectly. I mean, it works okay-ish, but, you can always, what one can always try to do, one can always try to see, how it could be done better. Let's try to do the following thing also, just for fun of it. Let's try to see kind of something like this. What do you say? Before we go for the break, let's do something like this. The only thing is, do we have a matplotlib here? No. So we need to import it before it breaks down. Import. What is POT? Yes. Okay, figure size. Actual with prediction of wine quality. Yeah. So here is the actual wine quality. Here will be predicted wine quality. And now what we have our, where is our predictions? We have never even stored it anywhere. Yeah, we just have it like this. Okay, let me just grab it from here. Okay, predictions are going in here, and the ground truth is going in here. And let's see how it looks like. Okay. Okay. So, and what does it telling us? Okay, because the wine quality is given by the fixed values. Okay. Obviously, clearly, there is a trend, and we could see it. But also the problem is that our model is predicting the continuous value, while the wine quality should be a discrete value. But that we can also address. Okay. So I think we need to go for a break, for the lunch break, and afterwards, yes, we can continue with classification.